Hey all, today we're going to talk about scatter plots, something you are probably have some familiarity with, but is important in statistics. So scatter plots are now where we're going to take two quantitative variables and try to see if there's an association between them. So we'll create some scatter plots in class and look at the association between some quantitative variables. But now let's talk about describing scatter plots. Three things you'll want to talk about when describing them are their direction, positive or negative, up to the right or down to the right. You want to talk about the form. Do they form a straight line path, a curved path, or maybe there is no form? And strength, we have strong, moderate, weak, or potentially no association between the two. So we want to describe some of these scatter plots, and just a quick side note that the x variable, or the x-axis, we call the explanatory variable. The y-axis we call the response variable. And so if we look at plot A, this relationship between women's clothes costs and food costs, we can see that it has a positive relationship. It's linear. We have a straight line path here that's forming, and we would say that it has moderate strength. Okay, there are areas where some of these data points aren't packed in as tightly, and so it's not really strong, but it's a moderate strength, positive linear relationship. In B, it's going to be a negative relationship because it goes down to the right, and we would say it's curved, and that it's pretty strong. These data points are pretty packed in tight to each other to this curved path. In C, it looks like we have a negative relationship. It looks like as working hours go up, the clothes index is going down. It has a sort of linear path. Looks like we might have a point up here that's concerning. And it's got a weak relationship. These data points are not packed in very tight. Last but not least, vacation days and food costs. There doesn't appear to be any association here. It's just a random scatter of points. And so we would just say that there doesn't appear to be any association. So we like to talk about correlation, and what correlation is the measure of strength of a linear, specifically linear. We're going to be talking about linear associations between two quantitative variables. And we have to check conditions in order to talk about correlation. The first condition is that the variables must be quantitative. The next is that when you look at a scatter plot of our data and these two variables, that it's got to be linear. And then we want to have no outliers. So if we have those three conditions met, we can talk about a correlation between two quantitative variables. Some properties of correlation. A correlation coefficient, we give it the letter R, and its sign tells you the direction. So positive means up to the right, negative means down to the right. The closer you get to 0, the weaker the correlation. The closer you get to 1 or -1, the stronger the correlation. So it's always between -1 and 1. There are no units attached to correlation. The relationship between x with y is the same as with y with x. If you scale data, meaning maybe you change the units, from kilograms to pounds or something like that, it's not going to affect the correlation. This, again, we're measuring the strength of a linear association, so not any sort of curved associations, just linear. And this correlation is sensitive to outliers, which is why we need to satisfy the no outliers condition. So we're going to create some scatter plots in class together, but I want to show you an example of one and then talk about its correlation coefficient R. And so this is on page 157. We're measuring different types of blood pressure, diastolic and systolic. And so if we want to be able to talk about the correlation, we need to first check the conditions. So we would look at a scatter plot of the data, and they have one for us. And it does look like we have a linear relationship. Both of these blood pressures are quantitative, so we've met the quantitative variables condition. It's straight enough, it's linear, we've met that condition, and there aren't any data points that are too concerning. Some of these are a little bit off the beaten path, but we could say that there's not really any outliers. And so if we had this data that we can plug into technology, specifically our calculator, we could calculate an R value, a correlation coefficient, and what they got was 0.792. So it's positive, which is what we see. This goes up to the right. As diastolic blood pressure goes up, systolic blood pressure also goes up. It looks pretty straight, so we're getting close to 1 here. 0.792 is closer to 1 than 0. And so when we were describing scatter plots before, we can see the connection between an actual value and actual correlation coefficient here. If it were 1, it would be a perfectly straight path, and we're probably not ever going to see something like that. And the last thing to say here is that it's very important to know that correlation does not mean causation. We have to be careful for what we would call lurking variables, something else present that could affect a relationship between two quantitative variables. And we'll talk more about that in class and talk about some examples of that. But it's really important to know that just because two quantitative variables have a correlation, that does not mean that one causes the other. That's the end. No questions today. If you have questions, please ask in class, and we will talk about this topic.